On a bitterly cold January morning in 1943, specifically the 16th day of the month, a newly constructed cargo vessel sat peacefully moored at a commercial dock in Portland, Oregon. The morning temperature hovered around 28 degrees Fahrenheit, and a thin layer of frost covered the dock's wooden planks. The ship was barely 10 weeks old, having been launched in early November from the massive industrial shipyards of Henry Kaiser that had sprung up along the American West Coast like steel forests. She represented the cutting edge of wartime industrial production, a testament to American manufacturing prowess. The morning atmosphere was unusually still and eerily quiet, with not even a whisper of wind disturbing the glassy calm surface of the harbour water. The sky hung pale and grey, typical of Pacific Northwest winter weather, with low clouds promising rain or perhaps snow later in the day. No storms threatened on the horizon. No enemy submarine prowled the depths beneath her hull in these protected coastal waters, and no visible danger presented itself to the crew or dock workers going about their morning routines of maintenance and cargo preparation. The crew had actually been celebrating just the night before, relieved to have completed their shakedown cruise without incident. They had toasted their good fortune in a local tavern, confident in their vessel's strength and grateful for their assignment to coastal waters rather than the dangerous Atlantic crossing. Some men were below deck preparing breakfast in the galley, the smell of coffee and bacon wafting through the narrow corridors. Others were on deck performing routine inspections, checking lines and preparing for the day's scheduled maintenance work. The officer of the deck was completing his log entries, noting the calm conditions and routine status. Everything appeared normal, mundane even, just another ordinary morning in port. Then, without any warning whatsoever, without even the slightest tremor or preliminary sound, the oppressive silence was shattered by a sharp metallic crack that echoed across the entire harbour like a rifle shot, causing flocks of seagulls to scatter into the grey sky and dock workers to freeze in their tracks, tools falling from startled hands. Within mere moments, something absolutely unthinkable occurred, something that defied every principle of ship construction and maritime experience. The vessel had completely fractured in two, her hull splitting catastrophically from the main deck all the way down to the keel, the thick steel plates tearing apart as though an invisible giant blade had sliced cleanly through her spine with surgical precision. The sound of rending metal was described by witnesses as both deafening and surreal, a screaming tear that seemed utterly impossible for something so massive and solid, a sound that would haunt their nightmares for years to come. Crew members standing on deck froze momentarily in complete disbelief, their minds struggling desperately to comprehend what their eyes were witnessing. Some later reported that time seemed to slow down, that they watched in horror as the crack propagated along the hull faster than they could run. Then survival instinct kicked in, and they scrambled desperately for safety, running toward the gangway, some even jumping the considerable distance to the dock in their panic. The bow and stern sections sagged in opposite directions like a broken spine, the metal groaning and shrieking as internal structures collapsed. The ship's structural integrity gave way completely, while still safely tied to the pier with heavy mooring lines, an occurrence so bizarre and unprecedented that it defied all conventional maritime experience and understanding. Men below deck found themselves trapped momentarily as bulkheads twisted and doors jammed. Some crawled through rapidly narrowing spaces as the deck plates buckled beneath them. Miraculously, all crew members escaped, though several suffered injuries from falls and scrambling over twisted metal. The Portland harbour master, who had been working in his office overlooking the docks, came running when he heard the terrible sound. What he saw shocked him to his core. A virtually new ship, one that should have had decades of service life ahead, lay broken in two pieces at his dock. The two sections remained partially afloat, held together only by their mooring lines and some remaining internal piping and wiring that hadn't yet torn apart. Water was already flooding into the ruptured sections. The harbour master immediately ordered tugs to secure both pieces to prevent them from drifting and possibly sinking in the navigation channel. He then sent urgent telegrams to the Maritime Commission and Kaiser's headquarters, knowing that this catastrophic failure would send shockwaves through the entire shipbuilding industry. This catastrophic incident wasn't an isolated occurrence or a singular freak accident that could be dismissed as bad luck. During that same brutal winter season, multiple cargo ships experienced disturbingly similar failures that created a pattern impossible to ignore. One vessel fractured severely in completely calm seas off the California coast, with no external forces acting upon her. No storm, no collision, Nothing that could explain the failure. The crew had simply been steaming along when they heard the terrible crack and felt the deck shift beneath their feet. Another tanker, built using identical mass production methods at a different yard, cracked so badly and so suddenly while loading fuel in port that the entire crew abandoned the vessel in absolute terror, leaving behind all their personal possessions in their desperate panic to reach safety before the ship potentially exploded or sank. Some men dove into the freezing harbour water rather than risk staying aboard another second. Between the years 1943 and 1944, over 2,500 ships reported major structural problems of varying severity, including dangerous hull cracks ranging from a few inches to several feet long, deck fractures that opened gaps wide enough to see through, and catastrophic, complete splits that rendered vessels total losses. Maritime insurance companies were hemorrhaging money, and some threatened to stop covering these vessels entirely. 19 vessels split entirely in half, their massive steel structures simply coming apart at sea, sometimes within sight of horrified crews on other ships who could do nothing but watch and pick up survivors if any made it to lifeboats. 3 ships simply vanished into the cold, unforgiving Atlantic Ocean so rapidly and so completely that no distress calls were ever transmitted, no emergency flares fired, no lifeboats launched, and no survivors ever found. These vessels and their entire crews simply disappeared from existence, leaving behind only mysteries, unanswered questions, and grieving families who would never know exactly what happened in their loved ones' final moments. These disasters weren't caused by enemy torpedo attacks from German submarines, weren't the result of severe weather phenomena like rogue waves or hurricanes, and weren't due to navigational errors, groundings, or crew incompetence. The ships were failing catastrophically under their own structural stress, essentially tearing themselves apart from within through some invisible weakness in their construction. It was as if the vessels had a death wish, a structural suicide. Sailors whispered darkly in port taverns and crew quarters about cursed ships and vessels that were committing suicide, their superstitious fears growing exponentially with each new report of failure. Some men refused to sail on certain ships that had shown even minor cracks. Others wore religious medals and carried good luck charms. The psychological toll was immense. Crews began demanding hazard pay. Some experienced sailors simply quit, preferring unemployment to sailing on these potentially deadly vessels. Following the devastating surprise attack on Pearl Harbor on December 7, 1941, which thrust America into total war on 2 fronts simultaneously, the nation desperately needed cargo vessels to supply military forces across 2 vast oceans, and needed them quickly in unprecedented numbers that staggered the imagination. The scale of the logistical challenge was almost incomprehensible. Traditional shipbuilding methods, refined over centuries of maritime tradition, but inherently slow and labor-intensive, took approximately 8 months to complete a single vessel from laying the keel to launching, which was far too slow to meet the urgent demands of global warfare on an unprecedented scale. The German submarine fleet, organized into deadly wolf packs using coordinated tactics, was sinking Allied merchant ships faster than they could be replaced using conventional construction techniques, threatening to strangle Britain's supply lines completely and potentially starve the island nation into submission. In early 1942, German submarines were sinking ships at a rate of over 500,000 tons per month. At that rate, Britain would run out of food and fuel within a year. The situation was absolutely desperate. Military planners calculated that America needed to build at least 3,000 cargo ships and build them within 2 years to maintain the supply lines necessary for victory. Using traditional methods, this would require decades and labor forces that simply didn't exist. The challenge seemed impossible. Some naval officers privately believed the war might be lost simply due to inadequate shipping capacity, regardless of how many troops or weapons America could produce. A businessman and industrialist named Henry John Kaiser, who remarkably had never built a single ship before the war and had absolutely no maritime construction experience whatsoever, made a bold and audacious promise to the United States Maritime Commission that many experts considered foolishly optimistic at best and dangerously delusional at worst. He claimed he could mass-produce reliable freighters using revolutionary assembly line techniques, similar to those that had transformed automobile manufacturing. In Detroit during the 1920s and 1930s, Kaiser was known as a man who built the impossible. He had constructed highways through mountains, massive dams in impossible locations, and bridges that defied conventional engineering. But ships, The maritime establishment was deeply skeptical. Ships weren't cars. They faced stresses and conditions that automobiles never encountered. The ocean was unforgiving of shortcuts and mass production compromises. His sprawling California shipyards, particularly the massive facilities in Richmond that eventually sprawled across hundreds of acres, became centers of intense 24-hour industrial activity that dwarfed anything previously seen in American shipbuilding history. The scale was staggering. Where a traditional shipyard might employ a few hundred men, Kaiser's yards employed tens of thousands. Entire temporary cities of worker housing sprang up around the facilities. Thousands upon thousands of workers labored day and night in rotating shifts, with the facilities producing ships at speeds that seemed utterly impossible by pre-war standards, and would have been considered fantasy just months earlier. The welding sparks flew continuously like fireworks, creating a perpetual glow visible for miles at night. Factory whistles blared at shift changes, their sound becoming the rhythm of the community. Workers moved in coordinated rhythm like musicians in an immense symphony of steel, fire, and American industrial determination. The yards never stopped, never slept. When the day shift left, the night shift arrived. When one crew finished a section, another began the next. Kaiser recruited workers from everywhere. Men too old for military service found purpose. Women entered industrial work in unprecedented numbers, many discovering skills they never knew they possessed. African Americans found employment opportunities previously denied to them. Even some workers with disabilities contributed in roles suited to their abilities. The diversity was revolutionary for its time. Everyone was united by a single purpose: build ships to win the war. Kaiser's revolutionary approach was elegantly simple in concept, but absolutely radical in execution and scale. He replaced traditional time-consuming riveting, which required skilled workers to heat rivets and drive them through overlapping plates, with modern welding techniques that allowed for much faster assembly and required less specialized training. He used prefabricated sections constructed in controlled factory environments, where workers could specialize in specific tasks, instead of custom-built components assembled entirely on the shipway, exposed to weather and working at awkward angles. He borrowed the fundamental logic of Henry Ford's automotive production line, with its emphasis on specialized tasks, standardized parts, and continuous flow, and boldly applied it to maritime construction in ways that challenged centuries of shipbuilding tradition. By late 1942, his yards were consistently completing ships in an average of 42 days from start to finish, a timeline that would have been considered utterly impossible just months earlier, and which represented a revolution in maritime construction. Some traditional shipbuilders who had spent their entire careers in the industry simply couldn't believe the reports. They assumed corners were being cut, quality was being sacrificed, but the ships looked solid, passed inspections and sailed away. When one particular ship was constructed in just slightly over 4 days and 15 hours, setting an astonishing world record that made international headlines, it was celebrated as an industrial miracle and featured prominently in propaganda reels shown in movie theaters across America before the main feature. Audiences cheered as they watched the rapid construction sequence compressed into a few minutes of film. Women welders, popularly symbolized by the iconic Rosie the Riveter imagery that appeared on posters and magazine covers nationwide, became national heroes and symbols of the home front contribution to the war effort, though ironically most were actually welders rather than riveters, transforming raw steel plates into ocean-bound lifelines for Allied forces fighting on distant shores. These women came from all walks of life. Former housewives worked alongside former teachers, shop clerks, and farm girls. They wore heavy protective gear, worked in all weather conditions, and often dealt with skepticism from male colleagues. But they proved themselves through skill and dedication. Some became among the best welders in the yards, their work consistently passing the strictest inspections. America was replacing lost shipping tonnage faster than German submarine wolf packs could sink it, seemingly turning the tide in the critical Battle of the Atlantic that Winston Churchill later called the only campaign that truly frightened him during the entire war. The statistics were impressive and gave cause for genuine hope. In early 1943, American yards were launching ships faster than the Germans could sink them. The production curves crossed, and Allied tonnage began to increase for the first time since the war began. Military planners began to believe that victory might actually be possible. Then, without warning and seemingly out of nowhere, the miracle began to catastrophically unravel in a way that threatened the entire war effort. The ships started breaking apart not under enemy fire or harsh combat conditions, but under their own structural weight and the ordinary stresses of simply sailing in cold water. Naval architects and marine engineers with decades of experience were utterly confused and baffled because superficial inspections showed the welds appeared perfect and flawless to the naked eye, with no visible defects whatsoever. The steel met every single specification laid out in the detailed design documents. The fundamental blueprints were based on proven British designs that had worked successfully for decades without similar failures. Yet somehow, inexplicably, these American ships were fracturing like fragile porcelain cups dropped on stone floors, failing in ways that made absolutely no engineering sense and seemed to violate basic principles of materials science. The cracks almost always began in the same predictable manner and locations, which suggested a systematic rather than random problem. They initiated at the sharp corners around rectangular cargo hatch openings, around gun mounts and defensive weapon installations that had been welded to the deck, or along the squared-off edges where hull plates met deck structures at hard angles. These stress concentration points, with their sharp corners and abrupt geometry changes, became the initiation sites for catastrophic failures. Engineers later calculated that these corners concentrated stress to levels 3 times higher than the surrounding material. Once a crack began its terrible journey in the continuously welded plates, it propagated wildly and uncontrollably, like a living thing with malevolent intent. The welded construction carried no natural stopping point, no rivet hole or mechanical joint to break its devastating path of destruction. Rivets, which the welding had replaced, had actually provided thousands of natural crack arresters. Each rivet hole required the crack to restart, bleeding energy and often stopping propagation entirely. But continuous welds provided an uninterrupted path. Within mere seconds, a fracture could race the entire length of a 500-foot ship, traveling faster than a man could run, splitting the vessel completely in two before anyone could react or sound an alarm. Some survivors reported hearing the crack propagate, a sound like tearing fabric but amplified to deafening levels, racing past them faster than they could turn their heads. Urgent investigations began immediately at the highest levels of government and military authority. The United States Maritime Commission, under tremendous pressure from Congress and the military, summoned the nation's top metallurgists from universities and steel companies, the most experienced marine engineers from private firms and the Navy, and specialized naval inspectors with decades of experience to determine the cause and find a solution before the entire shipbuilding program collapsed. Teams of experts, often working around the clock, pored over fractured hulls under harsh floodlights that illuminated the twisted wreckage, crawling through the torn steel with specialized measuring tools, cameras to document every detail, and thick notebooks that became filled with technical observations, measurements, and theories. Government committees met in Washington in closed-door sessions to debate various theories, each with supporting evidence that seemed plausible. Perhaps the steel mills were providing defective materials due to wartime production pressures and reduced quality control. Maybe the welding techniques were fundamentally flawed because welders were trained too quickly without proper understanding of metallurgy. Possibly the basic design itself was inadequate for the harsh Atlantic conditions, despite being based on British ships that worked fine. Or perhaps careless inspection and inadequate quality control were allowing defective work to pass through the system. Some paranoid officials even whispered about possible sabotage by enemy agents infiltrating American shipyards, though no evidence ever supported this theory. But while committees debated endlessly in comfortable Washington offices and experts searched for definitive answers in laboratories, the breaking continued relentlessly and remorselessly. Ships kept splitting apart at sea and in harbor with terrifying regularity. Each failure was investigated, documented, and added to the growing file of disasters. Sailors whispered fearfully of cursed ships and bad luck, growing increasingly afraid to sleep below deck in their cramped berths, lying awake at night listening to every creak and groan, knowing that the hull beneath them, the very steel structure protecting them from the freezing ocean, might tear open without any warning in the cold black water thousands of miles from home, condemning them to almost certain death in waters so cold that survival time was measured in minutes. The psychological impact was devastating. Some men developed anxiety disorders. Others turned to alcohol to cope with the stress. A few simply broke down and refused to sail. The miracle of mass production, America's great industrial triumph that was supposed to help win the war and demonstrate the superiority of American industrial might, had somehow turned into a maritime nightmare that threatened the entire Allied supply chain and potentially the outcome of the war itself. Confidence in the shipbuilding program began to erode rapidly among sailors, officers, and military planners. Congressional hearings were threatened, with senators demanding answers and accountability. Military planners worried privately about whether they could rely on these vessels for critical amphibious operations being planned for Europe and the Pacific. Insurance companies began refusing to cover certain voyages. Some Allied nations requested that American ships not be used for certain critical cargo. The crisis was reaching a breaking point. Then, from a place and person that absolutely no one in authority expected or would have predicted, came the answer that would ultimately save the entire program and potentially change the course of the war. Her name was Bessie Hamill, though some records list her as Elizabeth, an ordinary welder working the grueling and exhausting graveyard shift from midnight to 8 in the morning at Kaiser's sprawling Richmond shipyard facility, specifically yard number 3 on the eastern side of the complex. She was in her early 30s, married to a machinist who worked in a different section of the yard, and had 2 young children at home being cared for by her mother during her work hours. She had taken the welding job not out of any particular passion for ships or metalwork, but because it paid significantly better than the clerical work she'd done before the war, and her family needed the money. She wasn't a formally trained engineer with university degrees from prestigious institutions like MIT or Stanford. She wasn't a scientist with research credentials and published papers. She wasn't a naval architect with years of maritime design experience and knowledge of advanced ship theory. She had never set foot in a naval architecture classroom or studied advanced mathematics, differential equations, or materials science. Her formal education had ended with high school, but she understood steel in the profound and intuitive way that only those who work intimately with their hands can truly comprehend and appreciate. She knew it by its distinctive sound when struck with a hammer, by the specific glow and color it emitted at different temperatures, ranging from dull red to brilliant white, by the subtle way it bent and moved beneath concentrated heat, by the feel transmitted through her heavy work gloves, by the smell of the metal and flux, by dozens of sensory cues that no textbook could fully convey. For 8 long months, night after night in the cold darkness of the graveyard shift when most people were sleeping, she had been welding hull sections and watching with growing concern a deeply troubling pattern emerge in the work being performed all around her. Every night she observed her crew members, following the procedures they'd been taught in their brief training, start their welding runs at the extreme edges of steel plates, positioning their torches at one end and moving straight through to the far side in one continuous, uninterrupted run as they had been explicitly instructed in the training manuals. It looked efficient and productive. The supervisors praised workers who could run long, continuous beads without stopping. As each completed seam cooled down from glowing orange to dull grey and finally to ambient temperature, a process that took only minutes. The steel contracted and pulled inward with considerable force, physically warping the surrounding plates and building invisible internal tension within the structure that would remain permanently locked in place. The metal literally pulled and twisted itself as it cooled, creating permanent distortions visible to a trained eye. Hamill watched plates that had been perfectly flat before welding develop waves and ripples afterward. She saw deck sections that no longer sat flush. She observed stress marks appearing in the paint near recent welds. She noticed with growing concern and increasing certainty that the mandated welding sequence made absolutely no mechanical sense from a practical standpoint. By the time welders finished one long seam and physically moved their heavy equipment to begin the next seam, the first seam had already cooled completely and locked enormous stress into the structure that twisted and deformed the surrounding plates. The ship was, in essence, being deliberately built with destructive strain frozen permanently into its very bones, its fundamental structure. It reminded her strongly of the common mistake of tightening the center bolts on a wagon wheel before securing the outer ones, something every experienced mechanic and farmhand instinctively knows never to do because it warps the wheel and causes eventual failure, making it wobble or even collapse under load. When she first voiced her concerns to her immediate supervisor, a middle-aged man with official authority but limited hands-on welding experience, who had been promoted from an administrative position, he dismissed her observations entirely and somewhat condescendingly. "You're just a welder, not an engineer," he told her bluntly and dismissively, making abundantly clear her place in the rigid hierarchy of the shipyard. "The welding sequence comes directly from the design office," he explained with barely concealed impatience, "from men with impressive university degrees, professional engineering titles, and years of supposed expertise. Your job is to follow instructions and meet your production quota, not question procedures or play engineer. But Bessie Hamill couldn't ignore what her experienced eyes saw night after night and what her skilled hands felt through the welding torch. The evidence was overwhelming and undeniable to anyone who actually paid attention to the metal itself, rather than the paperwork and production schedules. She began making detailed notes during her breaks, sketching the distortion patterns she observed, recording which sequences seemed to cause the most warping. She talked to other welders, finding a few who had noticed similar issues but hadn't spoken up. Intimidated by the hierarchical structure and afraid of losing their jobs by questioning authority. In November 1943, after months of mounting evidence and growing conviction that lives were at stake, she did something that was considered absolutely unthinkable for a woman in her position, especially during wartime when questioning authority could be seen as undermining the war effort and potentially even treasonous. She deliberately bypassed her immediate foreman entirely, violating the chain of command, and directly requested a formal meeting with the yard supervisors, the senior management who normally never interacted with floor workers. It was a bold move that could have easily cost her job and her livelihood, in an era when employment opportunities for women were already limited and challenging, when supporting her family depended on that paycheck, and when being fired for insubordination could mean being blacklisted from other war work. She didn't come to that potentially career-ending meeting empty-handed or unprepared, knowing she would get only one chance to make her case. She brought concrete physical evidence that couldn't be easily dismissed or waved away with theories and explanations. Over several weeks, she had created test plates that she had carefully welded on her own personal time, staying late after exhausting 12-hour shifts when her body ached and she desperately wanted to go home to her family, using scrap materials and borrowed equipment when supervisors weren't watching. Some sample plates were done exactly the standard way as specified in the official procedures that every welder was required to follow, and these were visibly and dramatically warped, twisted, and distorted. You could see the distortion from across the room. Other test plates were welded using her proposed alternative method, starting from the geometric center and working outward in a balanced pattern, and these lay completely flat, true, and stable with no visible distortion whatsoever. You could lay a straight edge across them and see no gaps. The difference was dramatic and unmistakable even to an untrained eye. When a skeptical supervisor finally agreed, somewhat reluctantly and perhaps more to disprove her claims than anything else, to personally observe her shift and see the problem firsthand in real working conditions, rather than simply reading reports or examining samples. He witnessed the issue with his own eyes in real time, and his skepticism began to dissolve. The welders, diligently following their official orders and doing exactly what they had been trained to do in good faith, were unintentionally torturing the hull steel with every pass of their torches. Each cooling seam pulled tighter and tighter against the surrounding metal, fighting against itself until the entire hull structure itself became a cage of locked-in tension, completely invisible to the eye but incredibly powerful, waiting for the right conditions to release catastrophically. Under close microscopic examination in the well-equipped metallurgy laboratory, with samples sectioned and polished for analysis, the fundamental problem became crystal clear to the experts who had been searching for answers. The mandated construction sequence trapped enormous residual stress, measured in tens of thousands of pounds per square inch, throughout the ship's entire body, at critical structural points, the sharp corners of cargo hatch openings, around the heavy weapon mounts bolted and welded to the deck, at deck joint intersections where multiple structural members came together. These accumulated stresses converged and concentrated to extreme levels that could exceed the material's strength. Engineers calculated that stress concentration factors at these points could reach 3 or even 4, meaning the local stress was 3 to 4 times the average stress in the surrounding material. When the completed ships met the freezing waters of the North Atlantic, where temperatures often dropped well below 40 degrees Fahrenheit and sometimes approached 32 degrees, hovering just above the freezing point of seawater, the very fundamental nature of that steel changed dramatically and dangerously. What had once bent slightly under pressure without failing, now stiffened dramatically. Its ductility, its capacity to absorb and distribute stress through plastic deformation, collapsed almost entirely. The hulls became brittle and fragile in ways that engineers working in California's mild, temperate climate where temperatures rarely dropped below 50 degrees, simply couldn't have predicted or imagined without direct experience in Arctic conditions. In relatively warmer water above 50 degrees Fahrenheit, metal deforms and bends slightly before breaking, giving warning signs like small cracks that grow slowly and absorbing considerable energy in the process. In brutally cold water below 40 degrees, it shatters suddenly and catastrophically with no warning whatsoever, like glass struck with a hammer. The contrast in material behavior was absolutely devastating to ship survival rates. A microscopic crack, perhaps only thousandths of an inch long initially, forming at the sharp corner of a cargo hatch or gun mount mounting bracket, became a destructive spark, racing along the ship's entire length when all the conditions aligned perfectly and catastrophically. In ductile, flexible steel at normal temperatures, that tiny crack would gradually fade and arrest, bleeding energy and eventually stopping. In brittle steel under severe trap tension in freezing conditions, it became a violent storm of destruction that fed upon itself. The stored energy in the stressed welds became fuel feeding the fracture propagation, actually accelerating the crack as it traveled. Cracks didn't crawl slowly, giving time for response or repair. They sprinted at incredible speeds measured in hundreds of feet per second, sometimes exceeding the speed of sound in steel, which is approximately 16,000 feet per second, feeding hungrily on stress concentrations that multiplied the local stress load threefold or more at crack tips. In the most severe documented cases that engineers studied in detail, the catastrophic fracture outran sound itself, creating a thunderclap beneath the surface, slicing completely through half-inch steel plate before human reflexes could even register what was happening, before a man could blink his eyes. The fate of that first ship in Portland suddenly felt tragically inevitable when examined through this new comprehensive understanding of the failure mechanism. Built during winter months when temperatures were consistently cold, her seams carried millions of pounds of frozen tension locked permanently into the structure from the day she was built. When the Portland morning temperature dipped to a frigid 28 degrees Fahrenheit, with the steel cooling to nearly the same temperature overnight, her hull essentially turned to glass, losing all ductility and toughness. A crack formed at a hatch corner, probably initiated by nothing more than the slight movement of the hull responding to tidal changes, and finding a continuous welded path with no interruptions or mechanical barriers, tore cleanly through the entire structure in less than 5 seconds. There were no rivet holes to mechanically break the momentum, no overlapping seams to halt the cascade of destruction. Within mere seconds, the ship was two separate halves drifting slowly apart, held together only by mooring lines and some internal piping, its destruction as silent and swift as the closing of a door, as final as death itself. Older riveted ships from the pre-war era didn't share that particular curse or vulnerability to catastrophic sudden failure. Their construction was naturally discontinuous by design, a feature that had been considered a weakness but proved to be a hidden strength. Each plate was a separate structural element held in place by literally thousands of individual rivets, each one installed by hand by skilled riveters. When a crack propagating through one plate met a riveted seam, it stopped cold at the mechanical discontinuity, unable to jump the gap between separate plates. The overlapping joints, though imperfect and requiring vastly more labor to install, inadvertently saved them from catastrophic failure. Even if one plate cracked completely, the ship remained intact. Welding, for all its tremendous efficiency and speed advantages that had made the mass production program possible, created perfect continuity throughout the structure, essentially a perfect uninterrupted highway for fractures to travel completely unimpeded from bow to stern, with nothing whatsoever to slow them down or stop their deadly progress. The fundamental strength of modern engineering and efficiency had paradoxically turned into its own undoing, a cruel irony. The very feature that made welding superior for production speed and efficiency became its fatal weakness in service, and the basic shape and design features of the Liberty ships only magnified the danger significantly. Their square cargo hatches, specified by British naval architects primarily for easier and faster loading operations in port and more efficient use of cargo space, became severe stress amplifiers in service at sea. Sharp internal corners, which looked neat and practical on design paper and made perfect sense to naval architects, proved lethal in practice, concentrating tension to deadly levels at specific points where the stress had nowhere to dissipate. Every ocean wave that flexed the hull, and in rough seas a ship might flex hundreds of times per hour, sent invisible stress tremors radiating through those corners like ripples in a pond. Combined with the cold-induced brittleness and residual welding stress locked into the structure, they became fractures simply waiting patiently for their cue to propagate catastrophically. Time bombs built into the structure. By early 1944, Henry Kaiser stood at a critical crossroads that would define his legacy and possibly determine his place in history. The accumulating data and failure reports, which arrived almost daily now, left him with no comfortable illusions or easy answers. His massive shipyards, the enormous pride of America's wartime industrial mobilization, and featured regularly in newsreels, magazines and radio broadcasts as symbols of American industrial might, had been systematically building steel giants with fatal flaws stitched directly into their structural cores. Every ship launched potentially carried the seeds of its own destruction. To continue production using existing methods meant consciously gambling with sailors' lives and risking the entire national supply chain that was keeping Britain alive and supplying American forces around the globe. The corrected procedures and new understanding were rapidly rolled out across all of Kaiser's shipyard facilities and soon adopted by other shipbuilders nationwide after the Navy made them mandatory. Detailed training manuals, running to hundreds of pages, were completely rewritten from scratch with substantial input from Hamill and other experienced welders who understood the practical realities. The new specified welding sequences became absolutely mandatory with no exceptions permitted under any circumstances. Government inspectors were retrained to recognize and enforce the new standards, with special emphasis on sequence verification. As winter gradually gave way to spring in 1944, the epidemic of catastrophic ship failures slowed dramatically, then nearly vanished entirely. The cargo ships that formed the critical steel lifeline across the Atlantic, carrying everything from ammunition to food to fuel to troops, were finally holding together reliably under even the harshest conditions the ocean could throw at them. The comprehensive test results were both absolutely damning of previous practices and revelatory about the true nature of the problem that had been killing ships and sailors. When Kaiser's team of expert metallurgists carefully examined hull sections built using the traditional welding sequences that had been standard industry practice for years, comparing them directly against identical sections constructed with Bessie Hamill's new methodology under identical conditions, the contrast was absolutely staggering and scientifically undeniable. In the conventional builds following standard procedures that had seemed perfectly reasonable, sensitive stress measurement gauges using electrical resistance and mechanical deflection, methods recorded internal residual tensions exceeding 30,000 pounds per square inch concentrated at key structural points like hatch corners and frame connections, like invisible fists pressing against the steel from within with crushing force, waiting for any opportunity to release explosively. But the sections welded according to Hamill's carefully prescribed sequence told a completely different story that excited and amazed the engineers. The same precision instruments, calibrated and verified, showed far lower stress readings, barely reaching 12,000 pounds per square inch, even at their highest measurement points. The steel composition was completely identical from the same batches. The chemical makeup of the welds was the same using the same electrodes. The plate thickness was unchanged. Yet the difference in structural integrity and long-term reliability was absolutely undeniable and dramatic. Some sections showed stress reductions of over 60% simply from changing the sequence. What had fundamentally changed wasn't the material itself, or the basic ship design, or the size of the welds. It was the choreography, the specific order in which concentrated welding heat met steel, and the deliberate rhythm of the skilled men and women behind the welding torches. This represented a profound shift in understanding about how materials behave under fabrication stress, a shift that would eventually influence all of manufacturing. Steel, engineers came to more fully appreciate through this painful lesson, is not truly lifeless or inert despite appearing so. It responds and reacts dynamically in its own way, expanding considerably when heated, contracting as it cools, responding dynamically to every fluctuation of temperature in predictable but previously underappreciated ways. Under a welder's torch, its temperature can climb rapidly above 2,500 degrees Fahrenheit, glowing brilliant orange-white like molten sunrise, bright enough to require protective eye shields or risk permanent eye damage and blindness. In that brief, intense inferno lasting only seconds at any given point, The molecular structure stretches and separates dramatically, the crystalline lattice expanding significantly, sometimes by as much as 1% in linear dimension. But as the metal inevitably cools back toward room temperature, losing heat to the surrounding air and adjacent cold metal, it shrinks back substantially, essentially yearning to return to its original stable state and dimensions. The thermal expansion coefficient of steel means it grows and shrinks measurably with temperature changes. When that natural contraction is artificially confined and restricted by cold adjoining plates that act as rigid anchors, preventing the natural shrinkage, the shrinking metal traps tremendous tension inside the hull structure, storing elastic energy. This becomes a coiled energy, completely silent and invisible, but nevertheless waiting and building, like a compressed spring. If the welding sequence doesn't allow that accumulated stress to dissipate naturally and gradually through the structure to areas where it can be accommodated, it becomes permanent, locked within the ship's structural bones. That hidden strain alone, trapped invisibly within the metal at the microscopic level, might not have immediately doomed these ships under normal conditions. But nature, as engineers learned painfully through the loss of ships and lives, has absolutely no mercy for material imbalances or locked-in stresses when conditions become extreme.